Yeah, okay. So I'm going to introduce the concept, what it's used for, and what other use of fit you can do for for training a deep net model. Okay, so first, why do we use augmentation? So, for example, the AlexNet, it's a convolutional neural net of 5 convolutional layers and fully connected. It has been trained for solving the image large-scale visual recognition challenge of 2012. And for that challenge, we had a label training data of 1.2 million images. But the model itself has up to 6 million parameters. So it's okay. The model has a lot of capacity to learn complex patterns, but it clearly is going to overfit because we don't have. So the number of images that we have for training is much lower than the number of parameters that we have. So ways of try to reduce the overfitting that the model is going to have. One way is, okay, so maybe we don't need that many layers. Maybe a simple model will do that. In the paper of Alex Kirchevsky, they show the effect of removing one of the convolutional layers. But it's actually, that's not the bottleneck, as Kevin mentioned before, because the number of parameters that convolutional layer has, it depends on the size of the kernel, not in the size of the image. So, and that, for example, for that layer represents 1% of the total amount of parameters that we have in that model. So really, the bottleneck is it's on the fully connected layers. Because it's a neuron in its fully connected layer is going to be a linear combination of all the neurons below that, and it depends on the size of the image. That in that example, the 3 last fully connected layers have 37 million, 16 and 4 million parameters. So either or trying to do a simple model, try to reduce the size of the image, but that's maybe gonna make us to underfit the problem that we want to optimize, because we are reducing the capacity of the model for learning to classify in this case. No? So another trick is, I mentioned yesterday, to apply the dropout during the learning. That is just to set to 0 the output of some of the neurons in the layers. And that actually is a good idea, because every time that so it's like training a lot of different models that they share the same weights, so that force to learn more robust representation, since randomly all the neighbors around the neuron can be set to 0. So it's forcing the network to learn more robust representation. But the bad side of this is like we need more iterations to make the model to converge. And yeah, here comes the augmentation. So if the bottleneck is, okay, we don't have enough training examples for learning, how in this case, how to classify, just build more images, synthetically make more training examples. And yeah, so one example here, we'll take the original image with the level that we know, and then just modify that by flipping or doing some random crops of the image. And that's just for building more examples. And in the paper of Alex Kirchev, I never say properly the last name, and the paper of AlexNet, we say like this. They apply that, and with this trick, they managed to increase the training size up to 2048. So that will help. Okay, it's not going to be probably enough, because it's still having 60 million parameters, but definitely it's helping. And what they do is, during training, they randomly flip the image and select random crops of size 224 by 224. And during test time, they apply always the same procedure, which is augmenting the test image in 10 by extracting the descriptor of the corners, of the 4 corners and the center, and then the same on the flip image. And that Café does that for you automatically. So there is, and another thing good of augmentation is that you don't need actually to store that. You can do all of this on the fly. So you don't need to store the huge data set that you are synthetically generating. Okay, that's another way to augment the image, just translating and flipping. You can also modify the channels, the color channels. And the idea here is that, okay, so is the object contains the image contains a specific object that should be invariant to different light conditions or even different modifications in the color of the image. So that's a good idea to make the model to generalize better. And that's regarding to avoiding overfitting, but actually you can use these augmentation tricks for when you don't have a labeled data set for training. If you have a lot of images but you don't have labels for it, you can use augmentation for optimize what they call a surrogate problem. That will be how to classify different images, but you don't care what's inside the image. You just want to classify different images. And in the paper, which is called Discriminative Unsupervised Feature Learning, with example convolutional neural networks, they apply that strategy. So the bottleneck is, okay, we not always have a large data set with annotations, and we want to build representations that are invariant to translations and difference in illuminations or color. So what they do is they optimize a surrogate classification task for building good descriptors. The idea is, given an image, they randomly select a point and then they extract windows around this point of 32 by 32. When I say random, it's not really random because they want to pick a part of the object or a part of the object or an object. So they just make sure that the window they are randomly selecting contains high amount of gradients. And then on these paths, they apply augmentation. So they modify the scale, they rotate the image, they apply they vary the color. And like this, they generate up to a synthetic 16,000 classes with 150 examples each. And that's an illustration of how the data looks when they apply that. So on the right, example of the different classes, and on the left, for one class, all the different members of the class. So they optimize for classifying these kind of images to build good descriptors. And they apply that and test as an unsupervised way of learning descriptors for classification. And okay, so their performance is this one. It's not as best as the supervised learning, but you can see here that it's quite competitive. And that's a strategy that you can really make use of it because you don't need any training, you don't need annotations for be able to learn a good descriptor for classification. And also for, they apply that for descriptor matching. And they show that they got better superior and shift descriptors. Yeah, so that's the idea. So augmentation is useful for avoiding overfitting where you are training a CNN model. And it's not only for that, you can apply that when you don't have labels at all for optimizing to distinguish between different classes. Yeah.